Good morning, my lovely 12s. Right, buddies, here we go. Next topic on our amazing matrix unit is matrix inverses. So this is a really important topic. It's actually really cool as well. I think it's cool anyway. Yeah, and it's going to unlock all sorts of really neat stuff for us. We can use it, how you will use it, how you know how it works so far, is you can actually undo transformations. So you know how you could take like a shape and then you would apply a matrix transformation to it, and it might create like a shear or like a reflection or a rotation or something? Well, if you know what the matrix is that did it, what you can do is you can come up with the inverse matrix in order to undo it. So that's pretty much what these matrix inverses are for. The very coolest thing that we can do with them is actually to do with simultaneous equations, and oh my god, they're powerful for that. Like, you will love that when we get to do that, but that's still not quite today. That's soon. Yeah, so anyway, here we go, my buddies. Let's check it out. So here's what I've got for you. I've just got a couple of 2x2 matrices here, and I've got a couple of 3x3 matrices here. Now, when you look at them, I've got them completely general, so it's A, B, C, D, and this one is A, B, C, D, E, F, G, H, I. Okay? So completely general, no numbers to them at all. And I've times them by these quite specific matrices that I've got them times by. I've got this matrix here. It's got 1s on the main diagonal and 0s everywhere else. Now, it's the same deal on the big one, too. 1s down the main diagonal, 0s everywhere else, okay? So these are special matrices, maybe. So here's what I'm going to get you guys to do. I want you to pause the video and just work out what the matrix multiplication becomes. So you guys ready? So you're actually just going to do it, okay? So 3, 2, 1, go. Okay, and you are back, my buddies, and I've had a tactical little sip of water. I like that. This is actually why I make you pause the video. Okay, so here we go, my buddies. When you times it out, you should have got this. Well, a times 1 is a, b times 0 is 0, so a plus 0 is just a. The second spot will be a times 0, which is 0, b times 1, which is b. This one here, c times 1 is c, d times 0 is 0, so it's just c. c times 0 is 0, d times 1 is d. A, b, c, d. Oh! That looks a bit familiar, doesn't it, buddies? It's become the original matrix again. So when you times by these 1s down the main diagonal, it became the same matrix again. I wonder what will happen in a 3x3. Well, a times 1 is a, b times 0 is 0, c times 0 is 0, that's a, and so on. B, C, D, E, F, G, H, I. You should have confirmed. Cool beans, my buddies? So what we found is these matrices here, the ones that have 1s down the main diagonal and 0s everywhere else, are really special. They're a matrix that if you times by it, nothing happens. So I'm saying that they're special. You might be thinking that's the opposite of special, that's ridiculous. But actually, it's a super important mathematical fact when that happens. These guys even have a name. These are called the identity matrix. Okay, it's called the identity matrix, and usually you give them a capital letter I when you're naming them as a matrix. That's an identity matrix, and so is this. You can have any identity matrix as long as it's as long as it is a square matrix. It would still work. So if it's a 4x4 one, there'd just be 4 1s on the diagonal and everything else filled in. So no trouble at all. Now, basically, this identity matrix is super important, and you'll maybe see why. What if I told you that there's something right? What if I told you that the 1 in multiplication is really important? Well, 1 in multiplication is really important because it's the number that you can times by, and then the thing doesn't change. Get me? So it's quite special. It's almost like an identity number itself. The 0 in add and subtract is also an identity as well. It's a really important number too, because if you think about the 0 in addition and subtraction, it's the number that if you were to like add it or take it from something, nothing changes. This matrix I is the equivalent of that, but for matrices. So it's quite powerful. Okay, I'm going to use I then in order to derive for you, or in order to give you evidence. And this topic's actually not too bad, so I am dragging it out a bit, I'm not going to lie, but it's important that you know where it comes from. But I'm going to use this identity matrix to make this make sense to you. So here we go. To start with, 6 divided by 6 is 1, okay? Easy peasy, just with numbers, nothing to do with matrices here. 6 divided by 6 is 1, absolutely, okay? The reason for that is when you do division, it's actually like 1 over in the multiplication. So 6 divided by 6 is actually the same as 6 times a 6, because a 6 is actually 6's inverse. It's multiplicative inverse. So what you're going to find is timesing 6 by a sixth, or 6 times 6 to the power of minus 1, well, you end up with this 1 at the end, which is an identity. The same way that 1, like these matrices, are identities. So I might be making this complicated, but it will make sense. You wait and see. Okay, so in terms of this maths I've just written out, this is just 6, okay? It's like the original matrix, like ABCD was up here. 6 to the minus 1, well, that's 6's inverse. It's the number that when you times by it, the 6 becomes 1. Well, guess what, buddies? This is the matrix. 6 is like a matrix, okay? Just pretend it's like a matrix. Well, if I can times a matrix by the matrix's inverse, then I should be able to get the identity to come out, and it's for the same logic as that. Okay, so this is it with numbers, and now we're going to make it work with matrices. Cool. So instead of proving it, because, okay, you can prove it, and I have proved it on a piece of paper, but it was taking a long time, and then I Googled the proof to it, and I was getting it right, but I was only halfway there, and it was taking a long time. So instead of proving it, I have a better idea. I can evidence it for you, so you won't need to take a whole million years in order to prove it. So let's go through the logic, and I'll give you evidence, and I'll tell you how to prove it, and you can prove it if you want. How does that sound? Good. Okay, so here's what it's like, buddies. If you have a matrix A, and I've done it generally because we're going to be doing some proving here, it's A, B, C, D, the general square matrix of A, a general 2 by 2 of A. Cool? Well, in theory, there'll be another matrix, which I'm going to call A inverse, or A to the power of minus 1, W, X, Y, Z, that, when you times this one by that one, you get the identity. That's what it actually means, okay, buddies? That's what an inverse means, okay? It's the thing that you can times by and you get the identity. Just like in multiplication, the 6 was times by 1/6, which is the inverse, to get to get 1, which is the identity. Cool, cool, cool? Okay. Now, if you want to prove it, here's what you do. You can go A, like times it all out and get algebra expressions for each part. You'll end up with 4 simultaneous equations, 1 equaling 1, 0, 0, and 1, and you can have an absolute nightmare rearranging with a whole bunch of simultaneous equations, and yeah, it's a fiddle. It works. That's one way of doing it. There's another way of doing it, which is called row reducing, which is something similar to what you've done with simplex. And it's really good. That's better than what the simultaneous equation way. It's less steps, but it's still also a nightmare, so it's not cool either, really, to do the row reducing. And we don't even do row reducing at year 13 level either, so it's not worth doing either. But if you want to go for it, that's cool. If you just want evidence, check it out. Here we go. Here's what I'm going to suggest to you. Here's the original matrix, A, B, C, D, and I want you to times it by this. Because is it A inverse? Maybe. So I've made up a different matrix for you to times it by. So D minus B minus C A. So it's the same letters as an A, but written just a bit different. Cool, cool, cool. Well, let's do it. Times it out, and you should pause between each step as well. So pause. What happens when you times it out? That's it. It becomes that. Cool. So that's what you get when you times it out in terms of algebra. But the thing is, though, AD minus BC, nothing special there. Minus AB plus AB, that's 0. CD minus CD, well, that's 0 as well. So you end up with that. Cool? Which is kind of getting toward the identity matrix, because these two are both zeros. The trouble is these aren't 1s. Unless, could they be? That's right, they could be 1s, because you can factorize that out. Because you can always pull a scalar out of a matrix. And this is common on these two, and zeros is common too as well, because it's 0. So, my buddies, that's what we've got. We've now got the identity matrix, okay? So, the A minus 1 thing that we times to didn't quite give us the identity matrix when we times A by it, but when you factorize this bad boy out, you do get it. Okay, it did turn into the identity matrix when you times this by this, but it just also, you had to pull that out too, unfortunately. But AD minus BC, have you seen that anywhere before? Does that look familiar? AD minus CD. Does that look familiar? Oh my gosh, yes, what is it? It's the, oh shoot, oh no, did I just erase a slide? Oh no! Oh, okay, that's okay, panic over, yeah. That might have ruined my flow a little bit, but that's okay. Have you seen that before? Yes, you have! It's the determinant! So, my buddies, when you times this by this, it didn't quite make the identity, but if you were to divide by the determinant of the original, it would have done. Which leads us to this. And this is what you actually have to do and know. And this is where it becomes just normal and logical, this lesson. So, here you go. If you want to find the inverse of a matrix, and the matrix is A, B, C, D, well, its inverse is going to be 1 over its determinant, and then what you do is you switch over the ones in the main diagonal, so can you see that D took over where A was, and A took over where D was? Swap the main diagonal, negative the other two. Now, this is true, provided that the determinant is not 0. Because if the determinant were 0, it would break maths. Okie doke. Because it'd be 1 divided by 0, and that's going to break maths. I think I can explain it in terms of area scale factor, I think, too. But remember how the determinant was 0? It meant that it had an area scale factor of 0? Do you remember that? And that means that whatever shape that you had got mapped onto a line. Well, say that your shape was the entire plane, okay? It was like an entire infinite two-dimensional plane. Well, every single point on the plane then will get mapped onto that one line, which means that if you're going to take the inverse, which means do the opposite, it would be trying to get the points off the line but back onto the plane. Now the trouble is, there's more than one point on the plane that gets mapped onto the same point on the line, which means that if you're going to take one of the points on the line and put it back to the plane, you wouldn't be clear of which point on the plane was the point that we were on about. So that's why you can't actually inverse something that has a determinant of 0, and that's a scale factor reason for that, just because it's not one-to-one, that, so you've got many points that map to one point on the line. Well, that means you can't undo it. You'll learn about that at the start of year 13. It's not a one-to-one function, which means you can't undo it. So, yeah, you're scuppered. But anyway, if the determinant is 0, you can't do it. If the determinant is 0, the matrix is called singular. I'm going to write that down. I don't even know if you need to know this, but I'm going to write it down just in case. Okay, if the determinant of A is equal to 0, that's called singular. Okay, singular. Okay, and if determinant of A is not equal to 0, well, it's just non-singular. Cool? Okay, singular matrices do not have an inverse. You can't undo the transformation from them. Non-singular matrices do have an inverse. So if they have a determinant, then you can undo them. Cool. So let's do it, buddies. So let's just get a little bit of a practice on. I'll do the... well, you can watch me do this, or if you feel comfortable, just pause and do it on your own too, if you like. Okay, so let's do it. Let's get the inverse of this one called A. Well, step 1, you need to know the determinant of A. Well, determinant of A is going to be minus 15 that way, minus 12. So minus 27, okay? Which means that its inverse, A inverse, is going to be negative 1/27th, because that's just from there, 1 over the determinant. And just do that thing that we just said, flip the diagonal, minus 3 and 5, flip them, and negative the other two, negative 2, negative 6. You don't even have to times the minus 1 over 27 in, because usually when you're doing inverse, matrix inverse, you'll end up timesing by stuff anyway, and having a 27th in is a pain in the backside to times with, so you might as well just leave it out. Okay, now B, I'm spotting straight away as I do it with you that I've got a mistake in, so here we go, just kind of like avert your eyes for a sec. Oh, yeah, there's a negative 6 there. Yeah, perfect. Cool, let's try that one. See if you can find the determinant, or find the inverse of it. Well, let's do it. First things first, find the determinant. Determinant B is equal to, that's going to be positive 30, take away 30, so the determinant is 0. Oh no! All that means that there's no inverse. Okay? This would have been one of the ones that mapped onto a line, and you can kind of tell because if you look at it, this one is just the top line is minus 2 times the bottom line, or the other way around. The bottom line is minus 2 times the top line. So yeah, they're multiples of each other, no inverse. That's going to mean a lot soon when we do simultaneous equations, but now it's boring, so I'm going to just skip on. It's got a determinant of 0, you can't do it. Oh dear. Okay, what about the inverse, or the identity matrix? What was the identity matrix going to look like, buddies? Well, let's try it. What's its determinant to start with? Determinant of I, the identity matrix, is going to be 1 take 0. So it's just 1. So it does work, so that's cool. So I's inverse is going to be 1 over 1 times by, flip the main diagonal, so that 1 becomes that 1, and make both of the zeros negative, so you get that, which means the identity matrix, the inverse of the identity, is just the identity. Oh, that's cool, buddies. But if you think about it, of course it is. What does the identity matrix do when you multiply by it? That's right, nothing. Yeah, it's the one that did nothing. When you times by it, it did nothing. It's like timesing by 1. It's like adding 0. It's the identity. It's the one that doesn't make any difference in the operation that you're doing. So to undo nothing, what do? Nothing. That's why I is its own inverse. Happy days. Okay, next one. Final one for the lesson. Let's check this bad boy out. It says that A is 11,362, and it wants us to find A inverse, if it exists, which it might do. Okay, so let's do it. Let's find the A inverse. Well, what's the first step then, my buddies? That's it, determinant. So first things first, get the determinant of A so we can use our formula. 11 take 2 is 22. Take away 18, so the determinant is 4, which means it does have an inverse. And let's do it. What is A inverse? Well, A inverse then, what you do? Can you remember? Yeah, 1 over 4. Switch the main diagonal. 2, 11, negative the others. Minus 6, minus 3. Cool? Should I times it back in? I mean, there's no harm in doing it, except for if you times it back in, it would just be fractions, which is harder. So, yeah, let's leave it. Okay, part 2. Okay, part 2 is where it gets good. Okay, this is interesting, actually. Well, it's all interesting. It's all very good, this topic. But, yeah, this is a bit interesting. Check this out. It says the point P is mapped to the point Q, 5, 2, under the transformation represented by A. So P is transformed by A, and it becomes Q. Yeah, P is... I don't know why I'm doing these different colors. P is mapped to... I'm confused. I had a reason for highlighting them, and I forgot what the reason was halfway through. The point P is mapped to the point Q under the transformation represented by A. Find the coordinates of P. Okay, now this, my buddies, could just be a simple matrix multiplication that you can do in a couple seconds. Now what I'm going to do with it, though, is I'm going to be slow and pedantic because I want you guys to get it. And in your books, in your textbook, they actually do a couple of algebra proofs with you, and I want you to be able to do them. So I'm just going to show you what it means. So first things first is you have to remember how to transform a point, which you do because it's last lesson and it's earlier on in the year you did that. But let's just say, I don't know, let's just say I was going to use the point 3, 4 or something was the point that I was going to transform under this matrix A. Well, you guys get that I would do that by doing this, right? You'd go 11, 3, 6, 2, and you'd whack the point to the right, 3, 4. You just represent it as a vector like that, so the x's and the y's match up. Remember? And that would be how you'd move the point 3, 4. You'd put it in that thing. And if you had several points, you would just make this matrix longer. Like you'd just have that matrix longer if you had to do several of them at once. So you guys remember all that, right? Okay. Well, in that sense then, here we go with, I'm going to do like a bit of an algebra. It's not a proof, but I'm going to do a bit of an algebra argument here. And then that way you'll be able to answer your own algebra arguments later. Cool. So it says P is mapped to Q under the transformation represented by A. So first things first is we're going to get A, and the point that it's moving was P. So it's AP, right? So that's like the A times by the point P, and it tells us that makes Q. Okay, and we want to know what the coordinates of P is. Now if we just treat it like algebra, we do know what A is, it's that whole matrix. We do know what Q is. Q is going to be the point 5, 2, but downward like that, like as a vector. And we don't know what P is, and that's the thing that we're trying to solve. Now, if it was regular algebra, it'd be easy, you just divide both sides by A. But because it's not quite regular algebra, what we're going to, because it's matrices, we have to remember that order matters with a matrix, okay? You can times A by its inverse in any order, and it doesn't make any difference. It'll still make the identity, but apart from something with its own inverse, it does matter the order that you multiply by, okay? So we have to multiply either on the left or on the right, okay? So here's what you're gonna do. What we're gonna do is, because we want P to be by itself, we're gonna multiply by A inverse, but on the left. Okay, guys? So I'll show you what I mean. There's A inverse on the left of A. P is still chilling there, which means that we have to put A inverse on the left of Q. Okay, so I multiplied in on the left. Okay, because that does matter. If I multiplied in on the right, then P would be touching A inverse, and they wouldn't explode. They wouldn't cancel each other out. So we had to multiply in from the left. Okay, you need that. You need that to work. Now, here's the thing. A is attached to its inverse. What happens when A is attached to its inverse? What does that become when something's multiplied by its inverse? That's it, it's the identity, because it undoes it, right? It's the identity. That's where the derivation, that's where the proof, if you chose to do the proof, that's where the proof came from, and that's also how that's all of our evidence and everything came from there too. So it becomes IP, and that's just going to equal A inverse Q. But when you times something by I, it's as though you've done nothing at all. So it just means that P is A inverse Q. Now, really for marks, you can start the question here and leave out everything that I just did above, but when they give you questions, it's like, show that A inverse B C Q inverse is equal to B blah 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 B C A B inverse, or something like that rubbish, then you're going to have to be able to follow the steps that I just did there. So whilst this question didn't need all of that work, we did it anyway, so that's good. Okay, so it says find the coordinates of P. Well, what that ends up being then is it means, well, take A's inverse and times it by the Q, which is right? It's like essentially saying undo Q, and you'll get it. Well, let's do it then. So P is equal to A inverse was a quarter, open bracket, 2 minus 3 minus 6, 11, and Q is the 0.52 vertically as a vector, or as a matrix, I should say. So P equals, leave the quarter chilling because I don't want to mess about with fractions, so I don't have to. This does work, the dimensions match, so let's check it. 2 times 5 is 10, so it's going to be 10, take away 6, which is 4. And then here we're going to get minus 30 plus 22, which is minus 8. Now we're going to put the quarter back in because it's just a scalar, it affects all of the elements. So this is just going to be 1 minus 2. Now it was on about a point, and we've got the answer as a matrix. So that means that P is actually this point here, 1 comma minus 2. So if you were to take the point 1 minus 2, hit up this transformation with it, you would end up with Q, which is 5, 2. So I hope that that's okay, my buddies. I hope that you like it. And are you ready? We're going to practice for a whole lesson. Shaboosh, 139, questions 1 through 12. And do go for the heavy, hard ones as well. I think you can do the hard ones, definitely. And there's some that are algebra proofy like this. I'd have a go at them too to make sure you definitely have your head around it. So that's it. That's it from me. And I shall see you next time. Bye, buddies!